Okay, we'll get the presentation started here. Luciano Belo is a professional HVAC engineer who joined IMI Hydronic in 2009. For the last 12 years, he has supported America's engineering in the design of HVAC plants and assisted contractors and commissioning companies in installation, balancing, and troubleshooting large installations. Today, he'll be presenting to you on perfect, good enough, hydronic control, an overview and illustration of the reasons, remedies, and technology necessary to perfect hydronic control using latest and greatest technology and controls. You'll be able to tell by his accent that he's from South Milwaukee. You can't recognize it, but Texas, there you go, that's what it is. But I give the floor to Luciano. He'll have time for questions when you're done. You're live, so go for it.
Thank you, Jonathan. Thank you, everybody, for being here. The accent is from South Texas, extremely south of Texas, 10 hours flight, so Brazil. So kind of thank you for the intro. And the presentation today is going to be about the low delta T issue reasons. I'm bringing 4 main reasons why we see the low delta T issue. Setting the design GPM in each coil, maintaining a stable differential pressure across the control valve for stabilization. Primary flow should be equal or higher than the secondary flow. Differential pressure controllers, that is this device here in branches or buildings that it could be solved. Pressure independent balancing control valve, and where to place a DP sensor to control the variable speed pump. So before we start talking about the low delta T issue, I'd like to first explain what is that. If you read some magazines, ASHRAE, NAB, you may hear about that before, the low delta T issue. Well, look at this example. We have a 200 tons capacity chiller, 10 degrees delta T in my condensing part, 85 to 95, and a 45 degrees supply to my system. If I do have my return temperature, chilled water, coming back at around the 55 degrees, I can achieve the COP, the coefficient of performance at my chiller of 5. The biggest picture, the biggest point for us to understand on this graphic is, as soon as my return temperature, chilled water, start getting back lower from my system back to the chiller, you start to decrease the chiller's performance. And in this example that I'm talking about, close to 4 degrees, 5 degrees lower than the design condition, you're losing 15% of the chiller's efficiency. The reason that happened is when you have the design condition, 45 degrees to 55 in this example, this dark blue line is the evaporating temperature inside the chiller. If my return temperature, chilled water, instead of 55, it starts returning to 52, the chiller needs to drop the evaporating temperature, and that's why it's working with a lower performance, decreasing the COP of chiller. The reason that I like to make this quick intro, it is to show the 4 reasons and how to tackle or how to solve that in a job site, or how to solve that in a real life example. So the reason number 1 is nothing that we can do in the job site depending on the installation. If we do have the 3-way control valves in the system, 3-way control valve, if you're not using the coil, so you have no heat transfer, all the water coming here, it goes back to the chiller, or it goes back to the chiller plant. So if it's a 45 supply, the return would also be 45 degrees. So nothing much that you can do if all of the control valves are three-way control valve. You're going to have the low delta T issue and waste a lot of energy on the chiller consumption. The reason that I have these two balancing valves right here, this balancing valve on the bypass, it is to match exactly the pressure drop of the coil. So if you have a coil with a 3 psi pressure drop, this balancing valve right here is going to match the same 3 psi pressure drop. So when my modulating control valve or my on-off control valve is changing flow between bypass and coil, it's not affecting the whole balancing in the rest of the installation. And this other balancing valve is just to equalize the pressure drop between the other units. So just to balance like normal balancing valve in the system. Reason number two, this is something that the BMS or the automation guy could change in the system. If you're changing the leaving air set point for a lower number. So let's say that the design condition is a 55 degrees leaving air set point. So you're getting the design condition of a 16 degrees chilled water delta T. If somebody changes the leaving air set point instead of 55 to 50, for example, a lower leaving air set point, you're damaging the chilled water delta T. And in this case, it goes to 8.5 in this example. So this case is just do not change that set point in the BMS or the automation. Otherwise, you're sacrificing the chiller's performance. Third reason, when you're thinking about the full load, I'm not talking much about the ASHRAE 9.1 and resetting the chiller set point at partial load. This is more towards the full load in the system. If you're changing, getting a warmer chilled water supply, so you're changing the supply temperature instead of 50 degrees, instead of 42 degrees to get the 16 degrees delta T for your design condition. Instead of 42, you change to 50, for example, a warmer chilled water supply for your system. You're also sacrificing the delta T performance in this case, or just wasting energy or wasting performance of the system when you do that. And the fourth reason, that is the one that we probably see the most in many job sites, it is the unbalancing system. If you do have an unbalanced system, you're also affecting the chiller's performance. In this example, right here on the right side, if you have a no balancing valve or the balancing valves are fully open, you are overflowing the first coils in the system. And when you do overflow the first coils, the water will be passing too fast inside the coil. And when the water is passing too fast, it doesn't have enough time for the heat transfer. So basically, the water's getting, if it's a chilled water application, it's getting colder for back to the chiller, or if it's hot water, it's coming hotter back to the boiler. So also another point that is important to highlight, when you look at this ASHRAE Handbook 2019, Chapter 38, if you do get a 200% of the flow, or 2 times the design condition of that coil specifically, you're only increasing the heat output by 6%. In other words, it's just a waste of energy getting a higher overflow in the coil. That works for heating and cooling. But this graphic, or this shape right here, this curve, it's more specifically for coils that you have the heat transfer between water and air. If it's between water and water, it is a linear output between flow rate and heat output. So no benefit of overflowing the coil. So that gives us the intro to first start discussing about balancing and how to equalize the pressure drops in the system. So I'm bringing this really simple schematic with only 4 terminal units. And each piece of pipe right there, I have a 5 feet pressure drop. So for the pump supply water for this first coil, I need a 20 to make this whole loop. And for the pump supply water for my last coil, I need 50. So with that, if I turn on my pump, I'm overflowing the first coil that was supposed to get a 10 GPM, is getting 17. And my last coil was supposed to get a 10 GPM, is getting 3. This was basically the reason that was created the first balancing valve. It was to equalize the pressure drops in the system. The first balancing valve was invented or created in 1957 in Sweden. And that was the idea, to replace reverse return system by a device that I can control the pressure drop that I can add on my installation. So when you look at this first balancing valve right here, I do need to close more, in this case at 31 feet to get the total at 51. And my index balancing valve, I'm getting 1 foot to also get the same 51. So all of them with the equalized pressure drops. The reason that I'm keeping the 1 foot in my last coil, manual balancing valves or any balancing valve, manual balancing valve does not have a requirement of minimum pressure drop. What is the requirement for a minimum pressure drop? It comes from the DP sensor that you are measuring on the valve. So most of the DP sensors on the market, it is around 1 foot as a minimum pressure drop. If you have a below that, you do have a lower accuracy on your measurement, not recommended. And the main equation for balancing is always focusing the flow. It's equal to CV times the square root of differential pressure. That's how we always calculate it to get the right GPM. So to achieve all of that, it's important to say that now these are many tools and devices that could be used to help improving time, saving time on the installation. The first one that I'm going to talk about is this one on the bottom right. This is a software that you can input all the project, all the pipe lengths, the pressure drop of the coils, elbows, all the accessories that you have in the whole installation. And the software basically gives you all the balancing valve positions. What is the set point for each balancing valve? And it is a free software, by the way. So you can just input all the project information. It does give you the pump head calculation, where to place a DP sensor to control variable speed pump, and also, I think the most important here, the presetting for each balancing valve in the job. So basically the software, it is calculating exactly the same as we see on this slide. The software is calculating the actual pressure drop in each piece of pipe of the whole installation to be able to determine what is the valve position in all of the coils in the installation. Another thing that is possible to do, it is with the balancing device. So a balancing device like this one, you do have balancing methods that can save time on the installation and how quick you can finish hydronic balancing. In this equipment right here, it does have inside a balancing method that is called TA wireless. And the wireless method, it is basically using a 2 DP sensors at the same time. And when you use a 2 DP sensor at the same time, the screen is divided by 2. So you see 2 measurements at the same time. And the methodology behind this software, it is you start always measuring on your last coil and you measure with the one before. When you match the same percentage between your last coil and one before, they are balancing between each other. It doesn't matter if it's exactly the 100% of the flow, but if it's 120%, 20% overflow, and 120% overflow, as soon as you move the one valve before, the 2 valves in the end will move proportionally up and down. So what that means is that we call the proportional rule. Everything upstream, the change that you're making on the system, that could be a balancing valve in this case, everything upstream will move at the same proportional if they were set it before. So the wireless method or methodology on that case, it's always starting from the back and setting these 2 devices right there at the same percentage. And when you go to the one before and you set it the same percentage as the last one again, the 3 balancing valves, they will have exactly the same percentage as well, because everything that you move upstream will move at the same percentage wise. So this is the logic behind the software to use this calculation right there. So you see that what is the biggest numbers that we have is not the flow rate. but it's just a percentage. It doesn't matter if it's the same flow rate, but what it matters if it is the same percentage. So even if the last coil is 2 GPMs and this one, or sorry, 5 GPMs and this one is 2.5 GPMs, we always look at a percentage, not at the flow rate, to use this balancing method. Other balancing device also has in the market automatic balancing valves. Automatic balancing valves, you're never able to measure what is the true flow passing through the valve. You always measure the differential pressure, and if it is between the range, in this case, 232 psi or 5 to 6 psi, if you're measuring between the differential pressure range, you need to assume that you have the right flow rate. Things that are always important to be careful. If the valve is installed backwards or if you have a dirt in the system, you may still find the same differential pressure, but you have no flow passing through the valve or something wrong going on. So it's always very tricky, these sort of devices, when you're commissioning or creating a tab report. And basically it is a cartridge that goes inside the valve and keep opening and closing to keep in a constant flow, also known as a flow limiting device. Not recommended when you have installations with modulating control valves, because if you do have a modulating control valve and automatic balancing valve in the same coil, as soon as the modulating control valve starts closing, the automatic balancing valve will open up at the same time. So they'll basically be fighting against each other. Automatic balancing valve or flow limiting device is always recommended for on-off application, water source, heat pump, or many cases as well, like cooling towers, but never with modulating control valve, because they'll be fighting against each other. The next part it is maintain a stable differential pressure across the control valve. For us, the extremely important part on that, it is many times we go to a job site and we see a control valve always hunting or always moving up and down, or up and down if it's a globe style, or if it's a valve, I would be always rotating, closing and open. What is important to discuss a little bit more on that is mainly a problem on the selection of the control valve. Nothing much that we can do on the job site. The only thing that we can do at the job site to help fixing a hunting in a control valve is when we are able to reduce the pump head. If I have a less pressure going to the control valve, you help the control valve authority. So if you look at the ASHRAE Handbook 2020, chapter 46, it discusses a lot about the control valve authority. In the simple words, control valve authority is the sensibility of the control valve. So if you have a 0 to 10 volt signal, so 0 to 10 volt signal range on the control valve, and you're sending 5 volts, you expect that the control valve will close at 50% and stay in that position. That'd be great. If you do have a poor authority on that control valve, you're sending the same 5 volts, the control valve would be closing, open, or hunting position. And the way that happens is, if you do have a control valve authority with lower than 0.25 coming from this equation right here, the pressure drop of the control valve fully open design flow divided by the pressure drop of the control valve fully shut, it should be higher than 0.25. If it is below, you have a poor control valve authority. On the tab or the commissioning part that is important is, if I'm able to reduce my pump head, I'm able to reduce this number at the bottom of the equation. So I'm also helping to improve the control valve authority, and the control valve should work better on that way. And the top part is basically on the selection. So the blue number, it is the selection of the control valve. Let's just understand how that will work, the graphical explanation on how that will work in the job site. So here we have on the top right, my coil, heat output, and the flow rate. My control valve is normally exactly the opposite curve from my coil. It's what we call the EQM control valve curve. So if I do need a 50% of the capacity in my coil, I only need a 20% of the flow rate. 20% of the flow rate in the control valve, you only need 50% of the opening to get the 20% of the flow rate. So what happened is when I combine the two curves, the coil with the control valve, I do get a global linear. So 50% of my coil capacity, I do need to open my control valve by 50%. This is the perfect control valve authority when you have that above 0.25. When you do have that below, what happens is it is a distortion on the control valve curve. So instead of the blue, now it's the red one. And what happened in this case is when you're combining the coil with a bad control valve authority curve, my global, it's not linear anymore. So if my global is not linear anymore, what's going to happen is at 20% of the opening of my control valve, I'm getting almost 40% of the capacity. In other words, is a small opening of the control valve, you're getting a huge capacity on your coil. So the control valve needs to close again, and needs to open again, and needs to close again. So this is the graphical explanation of hunting in a control valve. I'm not sure if some of you saw that before. A control valve always moving and never stopping the position that should be stopping. I'm sure that could be messing up with many installations when you have something like that happening. So let's talk about the differential pressure controllers. This is a great helper or a great thing for the tab guys. It helps a lot on the commissioning, on setting the right flow rates, because it's a way to get in a pressure independent branch. So as soon as you set the first branch in this installation, there's 4 units, and you set the differential pressure control of this branch, you can do whatever you want in the rest of the installation. It will never affect this branch that you set it before. As most of you may know that it does have a lot of interactions. If I close one balancing valve, it affects all the other part of the system. If I'm closing another one, it changes all of them again. So it does have a lot of interactions between the closing one side, increasing the flow on the other side, and the differential pressure controller making a pressure independent branch and avoiding these interactions during the commissioning. So at this example, to understand how it works, the concept or the mechanical parts of the valve, here I have the pump, 80.2 feet as my pump head. I have a 10.2 feet as my pressure drop here closer to the mechanical room and this part. So that makes me 70 feet of the differential for this first branch. There's a continuation for other branches right there. But in this first branch, I have 7 feet. These 2 valves are basically reducing the differential pressure from 70 to 28 and making the 28 stable for this branch. So this is how it works, the technology of a differential pressure controller. It is reducing the available pressure going to that branch and making that number stable. And by doing that, you get a lot of benefits. First, you improve the control valve authority. So if you look at this control valve right there, 7 feet pressure drop. If you remember the previous slides, the calculation of authority, it is the pressure drop of the control valve divided by the available pressure. So without the DP controller, it should be 7 divided by 70 feet. With the DP controller, it's 7 divided by 28. So 7 divided by 28 is a much better number than a 7 divided by 70. So you're basically increasing the control valve authority, making the branch pressure independent, even if you have manual balancing valves on each coil. So if you have different wings, different floors, different risers, as soon as you're done with that riser, you can open, close, or do whatever you want to do in the rest of the installation. That branch specifically will not change the flow rates because it's keeping a stable differential pressure right there. If you're wondering where the 28 is coming from, like what is the differential pressure that I need to make stable on my branch? This is exactly the pressure drop that you need for your index circuit. So if you do a simple math, 1.5 plus 4.5 plus 4.5 plus 6.5 plus 2 plus 8 plus 1, you get a 28. Or the same numbers, you get it from 1.5 plus 4.1 plus 7 plus 15.4, you get the same 28. So 28 is exactly the differential pressure that I need for that branch to work in the design conditions. It's exactly what we need. So you don't need more than 28 feet for this branch. So that's what the differential pressure controller is doing. It's keeping a stable differential pressure for that branch for exactly what you need. The mechanical of the valve. Here in this example, I have here my pump. The blue line is the supply. So here's a manual balancing valve, a capillary tube connecting the two valves, and this differential pressure controller always on the return. So there is a membrane right there, dividing the water from supply and the water from the return. The way that a valve works is if the water on the supply increase the pressure, and that could be by other branches shutting off or whatever you're doing in the rest of the system. But if the supply of this branch starts to increase the pressure, it will increase the pressure on this capillary tube, it will increase the pressure on the blue part of the DP controller and push the membrane down to also increase the pressure on the return to keep the same differential for the branch. Remember that we're always talking about differential pressure, not a static pressure. So if the pressure increases on the supply, the DP controller will increase the pressure on the return to keep on a stable differential pressure for the branch. And that's how you can keep in a stable flow for the installation. The opposite is also valid. If the supply decreases the flow, the DP controller will open in the return to keep the same differential pressure again. So another simple schematic with only 4 terminal units, 10 GPMs in each coil. If I'm closing the last one of my system, and I have only manual balancing valves, you're going to have overflow. So instead of 10, now I'm getting a 13 GPM in each coil. If I'm closing this by 50% and now getting 8 GPMs, I'm getting a higher overflow in the others. If I'm closing the third one, or the second terminal unit, I'm getting a huge overflow for the other two that is still open. With a differential pressure controller in branch, that is a pressure independent stabilization per se. If I'm closing one valve in the end, I'm not changing the flow for the other 3 that is still open. Closing the terminal 3 by 50%, still keeping the same flow rate for the other 2 that is still open. And again, this is a way to get in a pressure independent model, pressure independent branch for my installation. So this is all the topics. Like Jonathan was saying, that I'm going to send this presentation to everybody. So these bullet points is a lot of things that I was talking during the presentation. But the main concept, the main point that is important for us to understand is on this drawing right here in the bottom right. You do have a variable DP in your system. It could be during commissioning, during balancing, because of the interactions that you have when you're changing one part of the system, opening another part, or even the partial loads in your system. So you do have the variable DP getting to the branch. The differential pressure controller will make it a stable differential pressure getting into the branch. So basically keeping a stable differential pressure to that 3 coils in this example and making the branch pressure independent. So let's now talk about the pressure independent control valve. I'm sure that most of you heard or play with that before as well, pressure independent control valve for the hydronic. Just giving a little bit of history. Differential pressure controller, it was invented or created in 1993. Pressure independent control valve around the 1994. So almost the same timing between pressure independent and differential pressure controller, because it is exactly the same technology in branches or directly at the control valve. If you look at this blue channel right there, this blue channel, this is the capillary tube that we saw before between supply and return of the branch, or this capillary tube right there, connecting supply and return of the branch. On a pressure independent control valve that's everything on the same body, balancing, control valve, and differential pressure controller, the capillary tube is internal. So it's just a tiny channel that goes inside of the valve. But you have exactly the same things. So this black part right there, that is a membrane. And these white dots, that is the spring. It's exactly the same construction of a differential pressure controller. The only thing that is combining everything on the same body. So when you look at this pressure dependent control valve, so you have the P1, P2, and P3. So P1 is the pressure before the differential pressure controller. P2, it is the pressure after the differential pressure controller, this purple water, and also before the control valve, the balancing and control valve seat. And the P3, it is the third pressure outside of the valve, the outlet of the valve. What is the difference between this pressure independent control valve compared to any other pressure independent control valve in the market? This is the only one that you can measure the delta H, or the available pressure. It does have a function on this PT port right there. This PT port you can open with the Allen key and basically bypass the DP controller. And when you bypass the DP controller and you fully shut the valve, you are able to measure the available pressure. And what we call as available pressure is the pressure getting into the valve. That you can easily do that with a manual balancing valve. So you can basically fully close the manual balancing valve, measure the differential pressure. It's what we call as available pressure. What is the advantage of measuring the available pressure? I would say two, basically, for troubleshooting installation. First, when you try to identify what is your index circuit on your system. So basically the designer calculated the pump head thinking about one index path until your index coil for the whole installation. Could be the last one or not always, but it's one index coil. Contractors are always changing pipes, pressure drops in the system may not be the same one after construction. So advantage of measuring the available pressure is the lowest available pressure that you have on your coils. It is your true index coil, your true index circuit for the whole installation. So basically, when you guys are doing the pump optimization, you're finding your index coil, which one is the lowest, my critical path in my whole installation. And for example, I'm measuring 5 PSI on my index coil. This valve right there, like 1/2 and 3/4 inch, only requires 2.2 PSI. So that gives me a room to reduce my pump by 2.8 PSI and is still keeping all of my coils at the same flow rate, not affecting my whole system. So that's what we call as the pump optimization. So this is one of the advantages of measuring the available pressure, is to be able to find your true index coil for the whole installation. The second advantage, it is troubleshooting. If I'm measuring the available pressure on this coil, and I'm measuring the available pressure on the second coil, like on the next one, the difference between these two available pressures, oh, sorry for the recording. Those are reflection. So if you measure the available pressure on the first coil, and you measure the available pressure on the second coil, the difference between this measurement is exactly the pressure drop between the two units. So you can also find the problems of the installation. I can share one thing that happened with me in one of the installations that I was taking some measurements. It was a data center. So data center, you have many butterflies, you have many shut-off valves for redundance, so many things like that. And in one case, I measured a huge differential pressure difference between two units. They were fairly close. It didn't make sense, that huge pressure drop difference between the two units. But the point is, I couldn't see the pipes because it was right above the ceiling. So I asked the contractor, mechanical contractor, to take a look on that. And he found the butterfly valve at 45 degrees. So just taking a huge pressure drop And the way that I was able to find that is by basically measuring the available pressure on the two units and just thinking that it was a huge number to be true. You can find the clogged pipes. So if you're troubleshooting a really old installation and you're unsure about how the pipe is, like you have all the dirt, all the things changed in the pipes. So if you measure the available pressure between the 2 points, you can find exactly the 2 pressure drops on these pipes and compare to the real pipe or new pipe pressure drop. So this is the advantage of measuring the available pressure in the installation. And this is the only pressure independent control valve in the market that you can do that, measuring available pressure, because you have this PT port function that you can open and bypass the DP controller. Manual balancing valve, most all of them, they can do that because you have the PT port across the seat. Only Venturi balancing valve, you cannot do that because the Venturi, the shut-off valve or the valve is not across, the PT ports are not across the seat. It's not across the valve. But yeah, measuring the delta H or available pressure is always a great thing to do as a troubleshooting capability. Getting closer to the end of the presentation, primary flow should be equal or higher than secondary flow. Normally, on the primary side, we always have the right flow. Equipment manufacturer chillers or boilers, they will not start up the system if they don't have the right flow rate. So the biggest challenge is always balancing the secondary side, that I'm assuming most of you play much more time on the secondary side, more challenging, more equipment as well. So this is just an example of a balancing valve installing chillers or cooling towers, making sure that you also have the right flow rate, equal or higher primary and secondary side. And the last topic that I'm presenting today is where to place a DP sensor to control the variable speed pump. It may not be a directly question to some of you, but we got this. We got that from some tab contractors asking us before. I think this question floats around between designers, contractors, and where to place the DP sensor to control the variable speed pump. What we mostly hear in the market is the 2/3 rule of thumb. So place the DP sensor 2/3 of the installation to control the variable speed pump. Where the 2/3 rule of thumb came from? If you place the DP sensor right there, closer to the pump, you're basically getting your pump almost working at a highest speed almost the whole time, no energy savings, but you're always guaranteeing that you have enough water for the whole system. So that is kind of a safe bet. Just place close to the pump and that's it. But you have a zero energy savings, so that's bad when you're thinking about energy consumption. The reason that happened is, looking at this graphic right there at the bottom right. This is what is extremely important for us to understand is my DP sensor is right there, where I do have my biggest differential pressure in my system, that is my pump. At the design condition, so the 2 black lines that you see right there, that is the differential pressure going through my whole system. So all of my pipes pressure drops between my first coil and my index coil. So you have this huge pressure drop going from the first equipment until your last one. The difference that you see on these 2 green lines, it is when you have the low flow rates. When you have a low flow in the installation, because of this relation right there, the pressure drop is proportional to the flow square. Because of this relation, at low flows, you have almost no pressure drop in the system. A good example of that is if the design of a pipe of 1,000 GPMs, thinking about the pipe designed for 1,000 GPMs, if that exactly the same piece of pipe, you only get in 200 GPMs or 20% of that flow rate, what that means is you only get 4% of the design pressure drop because of this equation right there. pressure drop is proportional to the flow squared. So 0.2, that is a flow rate, 20%. 0.2 squared, it is exactly as a 0.04. So 20% of the flow rate only means 4% of the design pressure drop. That's almost nothing. That is a square relation. So when you do have the low flow in the system, and that's why these two green lines, they're almost horizontal. It's a 4% inclination per se, or like a really low pressure drop in my whole system. So my index coil, this one, it only needs pressure between the two black lines, but it's getting pressure between the two green lines. So it's getting a much higher differential pressure than actually needs. And that's why it's a waste of energy placing the DP sensor at the pump. If you place a DP sensor at your index coil, so here I have the example. My DP sensor is right there. Oh. My DP sensor is right there in my index coil, or right here in my index coil. At a low flow condition, then you see these two green lines right here. It is what it's getting for my whole installation. So what happened on this scenario is placing a DP sensor on your index line or index coil, you're saving a lot of energy, but you may have the problem of not having enough water in some of your coils, even the ones closer to the pump, not having enough water to supply, to get the output, the heat output that it needs. When you look at this part right there, this coil specifically, it needs between this black part and to the top black part, so it needs a higher differential pressure, but it's only getting between the two green lines. So what's going on is this control valve is probably fully open, asking for more water, and the pump is not giving enough pressure on that. A good example on this one, thinking about the hotel. Where you have the conference room at the first floor and many hotel rooms at the tower. And my DP sensor is right there at the last floor, and my mechanical room is in the first floor. What's going on is, if it is during business hours, so nobody's at the hotel, everybody's at the conference or conference room at the bottom. What happened is, at my index coil, it is a low flow, low capacity in my whole system. So it's only getting the minimum flow for the whole tower. But in my conference room that I have a lot of people, high load, I may not get enough water just because of the load in this example. So basically my whole system is running at a lower capacity, and my conference room is where I needed the highest load. The control valve is fully open, asking for water and not getting enough. So we saw this example happening before in real projects, and that was basically just changing the DP sensor location to fix the whole problem of the starving equipment. So when you're thinking about the 2/3 rule of thumb, basically the 2/3, it is a kind of a way to be safe and always getting enough water for everybody, and also a way to save some energy. So you're getting kind of a mid-term between the two. The best way to do it is always through the right calculation. Nowadays, there are softwares that can calculate what is the pressure drop set point that you need on the DP sensor, and what is the best location for the DP sensor on the installation. I swear that this is the last slide, and we can open for questions or for next step, but this is the last one, I swear. This is basically just with some equations or some calculations, where to place a DP sensor and how to calculate the position and the set point. So in this example, I do have my 4 branches with the 4 differential pressure controllers. My pump head, it is a 22 feet. So these gray balloons in each of them, it is a calculation of my available pressure that I need for each of my branches. So this one is a 22 feet. This one is 20, 16, 18. So it gives me that my pump head, I need a 22 feet because it's the highest one. I got a 22 feet by just summing the 9 plus 1 plus 1 plus 1 plus 5 plus 5, it gives me the 22 feet. So I know that my index path or my index branch, it is the bottom right one. So there's where I place my DP sensor to control my pump head because this is my index branch. Also extremely important to say is, we saw that happening before, but DP sensor should be always before the DP controller. Because if you place that upstream, the DP controller would be always measuring the same number. That should not be doing that way. It should be always before, like you have in this case. The DP sensor is a yellow thing right there, and the DP controller is right there. Never the DP sensor inside the branch right there. So I found my DP sensor location by finding my index branch. Now to calculate my set point, what should be the set point of my DP sensor? It is looking inside of each branch. So this branch requires 9 feet. This branch requires 5, 6, and 10. So 10 is my highest between the 4 of them. So 10 plus 1 foot of balancing valve and 1 foot of differential pressure controller, I need a 12 as my my highest pressure drop branch. So this is what gives me the calculation for the DP sensor set point. So basically this DP sensor right there, it is located on my index branch, but the set point, it is my highest pressure drop comparing the other 4 branches that I have. This is just a simple example with easy numbers to run calculation. Of course, there are softwares that can calculate that easily for the whole installation. So here's the variable speed pump, DP sensor, position, and minimum DP setting. So the position, this is the name of the branch. And the set point, it is a 54.4 because it is the branch A61. That is the branch with the highest pressure drop inside the branch. Not overall, but inside the branch, this one is the one that has the highest pressure drop or required pressure drop for the installation. That is a 54.4. That is the set point for this DP sensor in this example right there. Thank you for your time. It was 47 minutes, so I think it's good on that. Thank you, everybody. I think now opens for questions or. No questions means it was too bad or too good?
Perfect. Well done.
Thank you.
We'll talk about the loop quick.
Yeah, so the loop, we're gonna be here the whole day. If you guys wanna play, somebody stole the cord, we cannot plug right now. But we're gonna be the whole day and we can play and show some exercises. If you wanna play hands-on, yeah, that's what it's here for. Some of you may be in our training center in Atlanta. I'm not sure if some of you travel to there, but we normally held the NAB conference or NAB training at our training center. IMI Hydronic. It's a much bigger training center than that. Training loop, like 40 feet wall and much more exercise that you can do. The ones that never been there, invited right now. Thank you. Should we turn off here or no?
Yeah, but you got it.
There you go.